Hi, everyone. My name is Jace Warren, and I'm currently a software engineer at Savi Solutions. It's an honor to have the opportunity to speak with you, and today I will be talking about distributed, scalable, fault-tolerant video streaming with Riak Core, Elixir, and Kubernetes. That's quite the mouthful, but again, just want to say a big thank you to ElixirConf and my company for giving me the opportunity to do this, and let's jump into it. To quickly tell you a little bit about myself, I recently just moved to Dallas. It's now my home. It's a beautiful place. I love the warm climate. As far as my experience goes, I started working in Elixir 3 years ago. And even though I've been in the industry for 10 years, I really love the language. It's very beautiful. It's fun to work with. And I'm not really going back to any other languages. I haven't looked back. As far as social media goes, I don't really do very much in that area, but if you would like to find me, here are some of my links. So, to give a little background about us as a company, we are a small engineering team that does a lot of things centralized around video. We provide the customers you see here and many more with a video management system, which enables customers to easily access, download, and play all of their location video in the cloud. We also do interesting things with this captured video, like tying it to point of sale data, for example, to provide high risk transaction audit reports. We provide an event search, which allows customers to filter and view video clips related to major events throughout their day. And we do a lot of other things, a lot of fun and exciting things as well. And so, if any of you are looking for work, we are hiring. And if any of those items listed there look challenging, feel free to reach out to us. So, why even build a video streaming platform to begin with? There are many third party providers with much more funding and a higher volume of engineers set up to do a much better job than us. I mean, just to name a few, we have Mux. They have an incredible presence online. AWS Elemental Media Store. There's a company called Video Experts Group, and many others with great platform APIs already in place and ready to go. Also, video streaming at scale is notoriously difficult and can be very error prone. Things can get very resource intensive and expensive very quickly. Also, as mentioned earlier, we are a small team and our engineers are already pretty leveraged as is, anyways. So, the answer to that question and most questions is money. uh, so I'm going to be a bit vague here, but we've been very fortunate as a company, and we have a great overall team and have experienced tremendous organic growth. Also, that growth coupled with some very promising partnerships was stacking up in such a way that we would need to build a video streaming platform that could support hundreds of thousands of concurrent camera streams in a relatively short time frame. Again, why the need to build this video streaming platform? Unfortunately, at that scale, all third party providers for our business use cases proved to be too expensive. As a result, we had to try something else. And fortunately, after calculating cost analysis after cost analysis against various cloud providers and tech stacks, building proof of concept after proof of concept, we found a promising way to build the video platform our customers will need at the necessary price point. And then also, to reference my manager, there's also the programmer's credo on why we do things. We do things not because they are easy, but because we thought they were going to be easy, which is very much how this process goes and has gone for us. Now, I want to talk just a little bit about the world of video streaming. In this world, especially if you work with surveillance and closed circuit television cameras, it is not often that video will play straight out of the video camera within a device video player, or like from the camera to the video device player. Why? In most cases, video stream chunks transmitting out of the camera are not natively supported for playback in browsers, mobile devices, computers, and televisions. As a result, there are usually multiple stages at play here. Initially, there is what's called a first mile delivery stage that involves capturing content from a camera to an encoder, which in turn transmits the video over a network to a series of intermediary processes or servers. From there is usually a series of pipeline operations performed on the video, including transcoding, transmuxing, producing multiple bitrate outputs, captioning, thumbnail generation, CDN population, and more, in which video is ultimately prepared for device compatible playback. Once that video is prepared for that device compatible playback and the content gets transmitted to the end viewer, that is known as the last mile delivery stage. Now let's talk a little bit about streaming protocols. A streaming protocol is a standardized method of delivering different types of media over the internet. Essentially, a video streaming protocol sends chunks of content from one device to another. Streaming protocols are often used at the first and last mile delivery stages, like we saw on the last slide. In building a scalable video streaming platform, we had to evaluate various streaming protocol pros and cons and choose the right protocols for our business use cases. For example, HLS, developed by Apple, and will play back on most, if not all, devices. It's also arguably the most widely used last mile stage. However, compared to other last mile protocols, it can come with increased latency. There is also MPEG-Dash. It's also mostly used in the last mile delivery stage. It's developed as an open source industry standard alternative to HLS. However, it's not supported by iOS or Apple TV. Next, we have RTMP. It's mostly used in the first mile delivery stages by companies such as YouTube, Twitch, Facebook, and more. However, because it was developed by Adobe, in order to play in the browser, it requires Adobe Flash, which is no longer supported in major browsers, and as a result, it's not a great last mile delivery stage candidate. There is also RTSP. RTSP is great for first mile delivery stages because it remains the standard for most surveillance and closed circuit television cameras. But Android and iOS devices don't have RTSP compatible video players out of the box. We also have SRT, which is kind of the new kid on the block, competes directly with RTMP and RTSP as a first mile solution, but unfortunately, it's still being adopted as encoders, decoders, and players add support. And finally, we have WebRTC, which will work on all major browsers, but was designed for video conferencing and less for the type of scale that we would need. There are others, but they are not included in this presentation for brevity. So, what approaches did we end up going with in our video streaming platform? Really, a mixed bag. As far as first mile delivery stage goes, RTSP made a lot of sense for us because it remains the standard for most surveillance cameras and NVR devices. We also have open port and third party proxy scenarios, which really enable our video streaming platform to reach out and pull footage directly. RTMP push protocol really made a lot of sense for us as well because, as my colleague Austin Hammer mentioned in his 2020 ElixirConf talk, we have a fleet of edge devices sitting behind our customer firewalls, and RTMP enables our platform to kind of push that footage out from behind the firewall into our video streaming platform. As far as last mile delivery goes, even though HLS can have increased latency, it makes the most sense here because it will play back on most, if not all, devices. We also found that we can get HLS latency into an acceptable range for our customers by tweaking camera settings, such as like the keyframe interval setting. So now that we have had a refresher on the world of video streaming, let's talk a little bit about Elixir and what makes it such a great fit at the application layer, like the pipeline processing layer. For starters, our team was already using Elixir, and we are big fans of its Ruby-like syntax, pattern matching, and functional nature. Elixir is scalable. In our video streaming platform, we had to plan for literally hundreds of thousands of concurrent video stream processing pipelines. Elixir scales very nicely vertically by being able to run hundreds of thousands of processes on a single machine. Elixir scales very nicely horizontally because these processes can also communicate with other processes on different machines in the same network and coordinate video pipeline work across multiple nodes. Now, in video streaming, customers expect the video to always be up and accessible. Elixir provides supervisors, monitors, and more, which help us to monitor and restart these video pipelines back to a known initial state that can get the process back in working order. So it's very fault tolerant. And finally, Elixir runs on Erlang VM, which gives developers complete access to the Erlang ecosystem, meaning we can import and use a library like, say, Riak Core. Riak Core, what is that? Many who hear the word Riak immediately think of the distributed NoSQL key value data store of the same name. However, Riak Core is actually a distributed systems framework that forms the basis of how Riak, the database, distributes data and scales. This means similarly to how developers will use the Phoenix framework to build web applications, developers can use Riak Core to build a distributed system. It provides the basic blocks to build distributed services. It provides consistent hashing, routing, sharding, replication, distributed queries, and more. And what makes Riak Core especially interesting is that it implements ideas from Amazon's Dynamo architecture and exposes that infrastructure as a reusable library, allowing easy adoption in any context that can benefit from decentralized distribution of work. For example, we use Riak Core as a distributed video process handling system. Riak Core ensures video pipeline work is always evenly distributed and handled by the same nodes across our distributed cluster. As far as Riak Core goes, it also helps to know that when you're using it, you are in good company. Riak Core is battle tested and widely used by the companies you see here. And also, it doesn't hurt that it has near linear scalability. So, everything in Riak Core revolves around a circular key space, aka the ring, which is what we see here. For example, you'll notice this ring is divided into a fixed yet configurable number of partitions, also known as virtual nodes or vnodes for short. A vnode is nothing but an Erlang process responsible for one partition of the ring, not unlike a GenServer. A physical node, represented as different colors in the image, can and usually will host more than one vnode at a time. It is important to bear in mind that vnodes are not bound to a particular physical node. They can be relocated to other nodes as new nodes are added to or existing nodes are removed from the system via handoff. Riak Core uses consistent hashing to map keys to specific positions in the key space. This mapping determines what partition is responsible for this key. Hence, it also determines which vnode is responsible for that key. Part of the strength of Riak Core is how it enables scalability with small operational effort. And so in terms of handoff, there's really kind of two types of handoff that can happen here. There's an ownership handoff, and it happens when a physical node joins or leaves the cluster. In this scenario, Riak Core reassigns the physical nodes responsible for each vnode, and it executes the handoff to move the vnode data from its old home to its new home. And then there's also hinted handoffs. If there's vnode redundancy, when the primary vnode for a particular part of the ring is offline, Riak Core still accepts operations on it and routes those to a secondary vnode. When the primary vnode comes back online, Riak Core uses handoff to sync the current vnode from the secondary to the primary. Once the primary is synchronized, operations are routed to it once again. And it's also worth noting that ring sizes can be dynamically changed. When the ring size is changed up or down, the number of partitions in the key space goes up or down too. Riak Core will figure out how to move the vnode data around your cluster members as it conforms to this new partitioning directive, as it uses the resize handoff type to achieve this. Now let's talk a little bit about Kubernetes. What is it? Why is it useful within video streaming? For those of you who aren't that familiar with Kubernetes, also known as K8s or Kube, it's an open source container orchestration platform that automates many of the manual processes involved in deploying, managing, and scaling containerized applications. This means that you can essentially take a pool of servers, VMs, or uh, hardware and essentially make one big resource pool that you can use the Kubernetes API to deploy your containers to. Uh, what about Kubernetes specifically is useful to video streaming? Just to name a few things, it's really nice that Kubernetes is cloud agnostic, meaning we can build and run our cluster the same way on virtually any cloud provider. For Elixir applications, there is extremely useful abstraction called StatefulSets that I will get into in a moment here. If you're not really familiar with services, in Kubernetes land, services can be external or internal load balancers for routing traffic to your apps across your Kubernetes nodes. What is particularly useful here, as far as video streaming goes, is you can use different load balancer algorithms. For example, if you're routing an RTMP TCP connection and passing it through to an Elixir application, uh, you can set the internal load balancer on within your Kubernetes cluster to use least connections algorithm as opposed to, say, a round robin algorithm, which would be a much better fit in that scenario. And next up, Ingress. I'll go into more detail about this in a second, but there is a lot of power worth mentioning here. And as we can see here, Kubernetes also provides useful tools like volume auto scaling and these things called volumes, auto scaling, and these things called helms and operators. And so I've listed quite a few things here, and really we're just touching the tip of the iceberg. So getting into pods, deployments, and stateful sets, I'm not going to go too deep here just for time, but pods are basically the smallest deployable unit of computing that you can create and manage in Kubernetes. In terms of Docker concepts, a pod is similar to a group of Docker containers with a shared namespace and shared file system. Usually you don't need to create pods directly. Instead, you create them through deployments. And so deployments are basically just a declarative way to define pods and replica sets, with replica sets being how many instances of the pods you want to run in your Kubernetes cluster. And so on top of that, you have this really interesting concept of stateful sets. And so stateful sets is the workload API object used to manage stateful applications. It manages the deployment and scaling of a set of pods and provides guarantees around the ordering and uniqueness of those pods. Whereas with a typical deployment, when you deploy that, your pod's going to have a unique IP, a random unique IP, and a random name. And so with stateful sets, everything's kind of predictive and orderly and determined, which is very nice when we're trying to connect Elixir nodes here in a second. All right, so just to give a high-level overview of the power of Ingress. So one thing that is really cool is I mentioned earlier that Kubernetes is cloud agnostic. But what you can also do with Kubernetes, thanks to the APIs that are defined, when you deploy your Kubernetes cluster, uh, it will basically auto-provision a load balancer in the cloud provider that you specify, depending on how you set it up, which is really nice. You can even, in some circumstances, name those load balancers. You could have like zone 1, zone 2. And then also, when you're setting up those load balancers, it gives you the option to write your code once, and it will deploy the same way across multiple cloud providers. And you can select your round robin or least connections kind of routing algorithm, which is nice, especially for RTMP TCP connection. And then also, one cool thing about Ingress is you can just, within your markup, you can define unique routes to all of your different applications. You can pair it with Cert Manager, which will communicate with Let's Encrypt and basically generate SSL certs so that it can handle all of your SSL termination. Really, it's a very powerful tool to have in your video streaming platform. So next up is volumes. So this gets kind of interesting. So like I mentioned earlier, volumes in Kubernetes land are similar to volumes in Docker land. But what you can also do with volumes is you can set them up in such a way that they survive restarts in your Kubernetes cluster. So let's say you have an Elixir application, it starts up, it gets some state, it fails. When your Elixir or when Kubernetes goes to restart that application, its disk, its volume that's mounted to it will still be there and accessible to the application. One thing that's also really neat is you can have two containers that are sharing the same volume, which is really nice. You can have a file that's writing to disk here, or sorry, you can have a container that's writing to disk here and another container that's co-located and reading the same disk here and producing something else with it. One other thing that's also kind of neat is you can have your volumes be completely in memory, which is really cool and can get some interesting performance gains there. And so also auto scaling, you want to dynamically scale your Kubernetes cluster both vertically and horizontally? You can. So the horizontal pod autoscaler automatically scales the number of pods in a replication controller deployment, replica set, or stateful set based off of observed CPU utilization. So basically you can put in some restraints based off of CPU and RAM, and it will basically create replicas of your app to keep up with the demand within your cluster. Then there's also the cluster autoscaler, which increases the size of your cluster. And so there are pods. Let's say you have pods that failed to scale on, or sorry, failed to schedule on some of your nodes due to insufficient resources. This autoscaler can detect that in a new VM on which the pods can schedule and run. And so there's really some great options here to, let's say you have variable bit rates coming through your video streaming platform. Let's say at night, there's not as much movement in the video frames. And so as a result, the bit rates are just lower because not as much changes between the keyframes and P frames. And so in that case, maybe you just don't need as many VMs running. You can have this completely configured dynamically to kind of auto manage that process for you. Okay, so this is where Kubernetes gets crazy. So for those of you who don't know what Helm or operators are, Helm is essentially a package manager. With Helm, you can install charts which help you define, install, and upgrade even the most complex of Kubernetes applications, like databases, message brokers, and more. You can do a Helm install of an entire database. Operators extend the functionality of the Kubernetes API to create, configure, and manage instances of complex applications. And what that basically means is operators give you the ability to define and create anything you can think of and tie it into the Kubernetes lifecycle events. I believe at one ElixirConf, I remember seeing someone create a to-do list with operators, and that was really incredible. And so, for example, in our cluster here, we have found a great use in installing and leveraging the Kube Prometheus Stack Helm chart. This chart does quite a few things, like installing Grafana and Alert Manager, but it also installs a Prometheus operator. Now, what the Prometheus operator does is creates, configures, and manages Prometheus database clusters inside of Kubernetes. This means that the Kubernetes has been taught and educated on what a Prometheus database is, and you can basically tell your Kubernetes cluster dynamically to spin up and tear down Prometheus databases now. It's really dynamic and very powerful. And also, this is worth mentioning, thanks to all the hard work of, I'm sorry if I mispronounce this, A. Kutmos and his PromX library, all you have to do is install and configure PromX, leverage telemetry, and with with our Prometheus stack, we now have complete visibility into our Kubernetes cluster nodes and pods and Elixir applications with pretty minimal effort. So tying it all together, these are some patterns that we found in using Kubernetes, Elixir, Riak Core, and getting everything to work as expected within our environment. And so what we have done here is we use a stateful set instead of a deployment for deploying our Kubernetes pods and containers. And we also join our ring via a connector GenServer, which I'll get to in a second. And then we leave the Riak Core ring via what's called an Erlang SignalHandler, which I'll explain in more detail. So one of the first things we want to do is ensure our Elixir application is no longer configured as a Kubernetes deployment, but instead configured as a stateful set. The wonderful thing about stateful sets is that it gives our application some guarantees within Kubernetes. No longer will Kubernetes be spinning up our Elixir applications with random unique IDs and network identifiers. In fact, applications will now be started up with stable unique network identifiers. Our applications can now have stable persistent storage, which can persist across all rolling updates. We also get ordered graceful deployments and ordered automated rolling updates. What this means is we can now reasonably query the Kubernetes API server and reasonably determine which applications are our oldest. We can also sort our applications lexicographically. This means that we can always be certain which Elixir app is the best ring node to join within Riak Core. And by having a predictable ring node, this helps us to avoid net splits in which two separate Riak Core clusters of 2 nodes or more cannot join each other. Also worth noting, within a stateful set, it takes some time shutting down a Riak Core application because it has to hand off all of its vnodes onto another node before shutting down. And so what we want to do here is update the termination grace period seconds, which indicates to Kubernetes how long to give an application to shut down before actually sending a sig kill. And like I mentioned before, we want to set a value here that will give our Riak Core application ample time to hand off its virtual nodes and shut down. Otherwise, the state in those virtual nodes can be lost forever. Next up is an approach that we found extremely useful in allowing our Elixir application to join our Riak Core ring. What we ended up doing was setting up connector GenServer process that is supervised by the application supervisor of our Elixir app. What this connector GenServer will do upon starting up is query the Kubernetes API server to get a list of existing Riak Core applications it can join with. Because we set up these applications via Kubernetes stateful set config files, we can filter our applications by the oldest and easily determine which ring node we want to join so as to avoid net splits. Once we have selected the ring node, it is as simple as calling Riak Core join, Riak Core Clement plan, and Riak Core Clement commit. So what is essentially happening here is when we call join, we are essentially letting the existing ring know that we are here and we would like to join. By calling plan, we are telling Riak Core to build a new plan on how to redistribute the vnode partitions across our new node in our cluster. Occasionally, the Riak Core ring might be processing another node, depending on how many nodes we're trying to roll out at once, and it might be busy. And in that scenario, we simply wait via process send and we try again. Once the plan is finally ready, we commit. And upon commit, Riak Core gets busy and starts redistributing vnodes via handoffs across our new nodes that make up our Riak Core cluster. Just as a precaution, we also schedule on our connector GenServer to occasionally diff the existing ring against any deleted stateful set applications to ensure there are no orphans. Finally, we need to make sure that upon shutdown, Riak Core successfully hands off all of its virtual nodes before shutting down. And one approach we have found useful is to use the Erlang gen event behavior. which consists of a generic event manager process with any number of event handlers that are added and deleted dynamically. And so once we swap the default signal handler with our gen event process, we can now intercept and receive all SIG-term events that will be sent by our Kubernetes cluster. This means that when Kubernetes is performing a rolling update and gives our application the signal to shut down, we can intercept that signal and manually trigger a Riak Core leave event in which our application will hand off any existing vnodes. And once they are successfully handed off, it will shut down with this functionally in place. When everything finally comes together, Riak Core works beautifully. For a long time before setting up Riak Core, we were actually using Horde, and unfortunately, though we were leveraging the Delta CRD and attempting SIG terms and just trying to give it enough time to offload state before shutting down, our distributed cluster would still drop video streaming processes upon rolling updates. We actually ended up having to build a boot process that upon every fresh deploy and rolling update would ensure that each video streaming process would still be up and running. We also noticed that if we would try to deploy more than 2 applications at a time, Horde could get into a permanently broken state. However, once we replace that with Riak Core, as long as we don't experience any SIG kills, our application will keep our distributed video streaming processes up and running indefinitely without dropping a single process, which is incredible. But disclaimer, all the problems we experienced with Horde were quite a while ago, and I've since heard and read that those issues have been fixed, but Riak Core has been working so well and we have been so busy, I haven't really had time to go back and validate. I am still excited about the Horde project, and I do want to take it for another spin at some point, just haven't had the time. So that is pretty much everything. I want to say thank you to ElixirConf. I want to say thank you to Savi Solutions, my employer, for allowing me to speak and have time to speak. And again, want to mention that we are hiring.